The second part, okay, everyone, you can hear me, right?
Yes, doctor. Yes, I hear. We can hear you.
Yes, doctor.
No problem.
Clearly.
If I lost connection, please quickly call me, okay, or miss call, just miss call. Then I will realize. Oh, type what give a message in the WhatsApp group. All right. So if you look at this lesson, it is related to the solidification process. Okay. We call this as imperfection, meaning that it is opposite to the perfect. Okay. Opposite to the perfect. Okay. The learning outcome of this lesson is you should be able to explain the types of defect arise in the crystalline solid. Explain how the defect affect the material properties. Okay, the relationship between the defects. Okay, we have defects and how much this defect may influence the properties of your materials. If you want to understand your the property of materials, you must look at into the microstructure, and defect is one of the criteria that explain why the material give that kind of properties. And then number 3, explain the defects. Explain that, okay, you should be able to explain that defects are not necessarily undesirable. Okay, when we talk about defect, it is something ugly, it is something unwanted, but in this context, it is not necessarily undesirable. Maybe we really need it, or maybe we really purposely create. Okay, so as an introduction, okay, crystalline defects is lattice irregularity. So something wrong with the lattice. Okay, you know lattice, right? We learn about crystalline, lattice, constant crystal structure. So something wrong with the normal condition or perfect condition of the lattice. Okay, if you look at this figure, all right, you know that, okay, of course, if the corn, the grain of the corn arranged perfectly, it's like this. However, not always as perfect as this one. Okay, sometimes you can see the irregular or something disordered structure because of this forming a large grain, or maybe because of the vacancy here, because of the vacancy observed here. That's the reason this grain able to grow larger. Okay. Actually, of course, there is no such thing as a perfect crystal. These defects can affect the properties of the materials. Okay, there are several types of defects. One is the point defects. Okay, point defects means at atomic level of defects. Second is line defects. Okay. Third is planar defects, and lastly, volume defects. We have talked about volume defects in the previous lesson, in the casting. So the casting itself, when we solidify a molten metal, okay, the liquid of the metal turn into solid, they will produce some defects. So it is three-dimensional defects compared to planar. Planar is actually two-dimensional, and line and point is one-dimensional defects. So the point defects is actually at an atomic scale defects. So imagine this is the atoms bonded in the metallic bonding, and when we identify defects, we usually identify like this. Okay, for example, let's say the white atoms is actually the normal atom, the actual atoms, or the parent atoms. Okay, and then if you observe another irregular self, meaning that actually it's supposed to be in the white color. Okay, similar size. Okay, but I just want to highlight it that this I'm sorry, this one, okay, the first one, number one defect is self-interstitial. Self-interstitial meaning that this atom A and atom B is actually a similar atoms, similar materials, similar elements, except that the B atoms is actually a defect because it is not in the actual perfect or ordered structure. Suppose to if it is ordered structure, this plane of atom is perfectly planar, okay, lurus, okay, flat, all right. But what you can see now, it is not flat. So why? Because of the defect. One is known as self-interstitial. Dia terselit. Interstitial tu macam pencelahan lah. Alright. Self means the same atoms, same elements. If it is copper, means that the self-interstitial atom is also copper atoms. Okay. A and B is similar. Alright. If there is a missing atom, so we call it defect of vacancy atoms. Okay, vacancy. Why? Because there's no atoms here. Okay, it is known as vacancy. The next is substitutional impurity. Why we call impurity? Because this C atoms, C is not similar with A. Okay, let's say A and B is same. A is parent atoms, the majority of the atoms in your materials, and suddenly you have foreign atom, okay, where the size is larger than the atoms of elements A. So this guy is known as substitutional impurities. Okay, and that is substitutional means that it's replace the the spot of original atoms belongs to elements A. All right, so it requires vacancy of one atom. Okay, unlike substitutional impurity, interstitial impurity is basically foreign atoms that is having size smaller, much smaller than the atoms A. So let's say this is D, the size of D much smaller than A. Okay, the size of C just not similar, maybe larger, maybe smaller, slightly smaller, but atom D very much smaller than A. The difference must be larger than 15%. Okay, so now then it will become interstitial impurities. Impurities mean it is foreign atoms. Okay, next is ionic and covalent solid vacancy. So it's just moving from this side and moving to this side to obtain the most stable formation of ionic or covalent bonding with the neighboring atom. So it is still a B. This is considered B, which is the same as the parent atoms. Okay, it doesn't have a dimension defect, so it is at atomic level. So point defects actually distort the lattice and provide a way for atoms to move about solid. Okay, so what you can see, if it is this one is considered as a perfect. Look at this crystal structure. Okay, this one is almost perfect. However, if there is a like this one, okay, there is a defect. So what happened is this defects is actually distort the lattice and provide a way for atoms to move about the solid. Okay, so because of this defects. So what is vacancy? Vacancy is a missing atoms. Okay, and you can calculate by using these equations. You can obtain this equation in the textbook, Callister textbook. And following this equation is being derived as Q is activation energy. You can obtain from the experiments and from the database created by the experiments. And this is a Boltzmann constant of K. And how to determine N? N is the density of materials, Avogadro's number, and the atomic number. Okay. So it's highly influenced by temperature, where more vacancy can produce at a higher temperature, where at a high temperature, no, the influence by temperature because diffusion occur during because of the influence of temperature. Right, vacancy defects puts the neighboring atoms under tensions, reduction in density. Why it reduces the density? Because the space is still there, but the numbers of atoms is reduced. Okay, remember when we define density is something matter, okay, where it's of course includes the mass, okay, or number of atoms, okay, whatever physical matter observed divided by the space, okay, the volume itself. So if this guy, the group above this at the top part is less, meaning that the number of atoms is reduced. So what happen is the density will reduce. Okay, so if this guy is reduced, number of the atoms is reduced, so the density will reduce, of course. Large number of vacancy can reduce ductility, while increasing will reduce the hardness. Okay. In most cases, diffusion, which is mass transport by atomic motion, can only occur because of the vacancy. All right. Because yeah, of course, if you want to move to one spot to another spot, you have to ensure that yeah, for example, if you want to potong the line, so make sure kereta kat depan masa you drive kan, while you are driving, if you want to cut the line, so you have to ensure that there are enough space for your car to squeeze in the empty spot. Okay, so of course it's influenced by the vacancy. So diffusion may easily occur if you have a lot of vacancy. So if you want to create more vacancy, you can induce more temperature, so the vacancy will increase. All right, self-interstitial vacancy. Self-interstitial vacancy is a defect that caused by an extra atom, same as host atom, that has crowded its way into an interstitial void in the crystal structure. Okay, so actually there's no vacancy there. But because of the rearrangement of the its original atoms, so it's provide the vacancy, not the atom is missing, okay, but it's rearranged and provide some vacancy in it. Okay, so for example like this, okay, extra atoms is moving from here to here and it's occupied this area, so it provide the vacancy. This is interstitial. Interstitial, why? Because originally this is the space is like this, but this for example this guy go to this area and squeeze the neighboring atoms further away, and that's the reason it's create a vacancy. Okay, so the impurities, now we talk about when we add foreign atoms or allying elements. Okay, so impurity is not similar with the original elements of your materials. Okay, it can be done by substitutional or it can be done by interstitial. Okay, depends on the application or the properties that you want. All right, substitutional impurities. Substitute means that you need to replace. It's require vacancy. Means that the vacancy is replaced by the impurities. Okay, so a substitutional impurity atoms is an atom of a different type than the bulk atom. Okay, the parent atoms, the parent materials. For example, you have copper, and then it's been the vacancy of your copper atoms is replaced by the impurity. Okay, like this. Okay, it seems like let's say this is metal A and this is metal B. Okay, metal A seems positioned at exactly the position of its original atom, which is B. Okay, so the A is the blue color is impurity atoms. Okay, and the white color is host atom. Okay, the blue color is placed exactly at the original position that belongs to the white atoms. Okay, atom. Okay, the size about the same. Then only it will behave like this. Okay, but to allow these substitutional impurities, there are some requirements. Okay, the size must be no more than 15%. Okay, if it is larger than 15%, okay, uh, it will um, it will very difficult this atom to uh, mix together, forming the substitutional impurities. Okay, so and beside the valency must be the same. The valency means that, for example, like nickel, when it's being ionized, it will become 2+. This is the valency condition where atoms at the valence atoms is 2, and then copper also have 2+. How about aluminum? Aluminum can form 3+, because it has a valence atoms equal to 3 electrons. Valence electron. Okay, the valency. So meaning that this 2+, 2+. If we look at this nickel 2+, copper 2+, this nickel and copper, if you try to mix nickel and copper or nickel and aluminum, you will find that nickel love copper more compared to aluminum. It tends to form alloys. It can mix with copper as much as possible. However, if a nickel try to mix with aluminum, it will has a certain limits. Okay, maybe you can mix nickel and aluminum, but not 100%. Okay, so unlike copper, nickel and copper, it can merge. You can add copper 1% in nickel, 2%, 3%, 4%. In fact, 50%. In fact, 99.9%. So you can still mix this, but for aluminum, it has a limit. So many limits. If you try to mix more, it will form another phase. It is not as easy as uh, nickel and copper. Why? Because of the valency. Okay, must be similar. Okay, so number 3, the rules for allowing the substitutional impurities. Okay, if you want to making alloy, so you have to ensure this. If your alloy require properties that only belongs to only can be obtained by mixing, forming a solid solution, or let's say this, or yeah, the properties only can produce by substitutional impurities. So you have to ensure this rule. Okay, the size between the atoms must be not the difference must not more than 50%. The valency must be the same. Crystal system must be the same. If nickel has FCC, copper also has FCC crystal system. So nickel and copper much yeah can mix more between them. And then electronegativity must be comparable. Okay, for example, copper and nickel. What is the electronegativity? Or look at the size. If you try to measure the a percentage difference between nickel and copper, you can see it is less than 50%. And this one, both have FCC. This is electronegativity. It's almost consistent. Okay. And another one is interstitial impurity atoms. Okay. For interstitial, it is if you look at the previous explanation, Okay, this will yeah, because of it is much smaller, it can fit in at any empty spaces. Okay, let's say for this atomic arrangement, normal atomic arrangement. Okay, it's space is there. Okay, so if you have very small atoms, this atom can fill in all the abundant spaces. Okay, abundant spaces between the parent atoms. Okay, interstitial impurities atoms fit into the open spaces between the host atoms of the lattice structure. Okay, interstitial impurities you can see in the atomic structure of this BCC. Okay, this is BCC. How is formed um, uh, the tetrahedral position or octahedral position because of the impurity. So it will form another crystal structure inside the BCC. Okay, because of this foreign atom. Okay, so because of interstitial phenomena is only applicable for small atoms. So basically, if you do alloying elements considering hydrogen, carbon, nitrogen, or oxygen, you will obtain the alloying the structure inside the alloy is through the interstitial impurities. So when we talk about impurities, is something not pure. So not pure means that the non-pure condition is actually a good way to create alloy. Okay. Okay, sometimes we have a Shopsky defect. This is a vacancy defect found in ionic solids. Okay, for example, the missing of Cl. Okay, to balance the electrical neutrality of the compound, an equal number of anion and cation will be missing from the compound. Okay. Like this. Okay, in the magnesium chloride, due to this vacancy, the density of solid phase is less than the theoretical density of the material, similar to metal. So when iron, also the missing Mg and Cl. Okay, Frankel. Right, so this is another type of defects. Okay, anion migration creating vacancy in the silver chloride. Okay, the defect forms when an atom or ion leaf is placed in the lattice, creating a vacancy and lodge itself a nearby location. Okay, we have another types of defects. The main defects is the first four that I explained earlier, but this one is another category based on the different types of bonding, which is ionic bonding. Okay, the arrangement of ion, cation, anion, right? Okay, that's it for the atoms defects. Okay, alloy means there's a defect inside your materials, and alloy basically can produce better properties compared to pure metal. Okay, for example, steel. We never use pure iron. We always use iron carbon. Whatever steel that you use in our daily life, it is iron plus carbon. There's no such pure iron. Okay, so yeah, that's it. So meaning that it is defects, of course, but it is very benefit and widely used in our daily life. Right. So next is line defects. Just now we only talk about point defects. Okay, now it is line defects. Okay, so this is a line defects. The dislocation. Okay, dislocation. It is a if we mention about dislocation, is actually yeah, dislocate, like you play football and you get injured because of the dislocation between the joint or something like that. So dia macam terkehel, right? Or in bahasa we call it kehelan, right? We have these terms in our language, which is kehelan, terkehelan. Right, this is a line defect within a crystal structure which contain an abrupt change in the arrangement of atoms. Okay, now we talk about atoms, but one set of atoms. These atoms is arranged. Okay, not one small single atom, but this is involve the arrangement of sets of atoms. Okay, the mobility of defects is actually counter the strength and the activity of materials. So meaning that the atoms in the metal, solid metal, okay, move. Okay, the behavior on how atoms move or set of atoms move is actually can reflect the strength and the activity of the materials. Okay, so basically we have two types of line defects. One we call edge defects, and another one is screw edge dislocation. Another one is a screw dislocation. Okay, dislocation. One is edge, one is screw. So the dislocation, edge dislocation, okay, it is actually can easily visualize as an extra half plane of atoms in the lattice. For example, okay, can you identify which one is the extra plane?
The middle one.
This
One,
one?
two, three. Ah, yes.
Yes, okay, good. So if we look carefully, this one is continuous, 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 one set, one set, one set. But this one is not. Okay, this one is not. These sets of atoms. Okay, on this plane there are extra half planes. Okay, so it is not continuous. Kalau dia continuous sampai bawah, maksudnya dia one set lengkap lah. But it's not extra anymore. But this one, if we look at this one is continuous, suddenly there are an extra here. Okay, which is not continuous through the down here. No. Okay, we don't have this part, the bottom part. It's only a top part. So so this one is the boundary here is a edge dislocation line, right? Edge dislocation line. So can you imagine suddenly there are an extra plate at this original position. Okay, it's like it's squeezing to the left and to the right. It gives some extra force. Okay, so it's macam ketat kat situ tau. Macam tu je ketat, right? So the defect, the dislocation means that dislocation tu benda yang akan terkehel tu will the dislocation phenomena will occur on the edge dislocation line, on this line. Okay, on this line, right? So if you give a force, because kawasan atas ni agak tense, you give force, it will moving this part. This part will move following the direction of the force. Okay, so this part will move. So move tu maksudnya terkehel lah, right? Okay. Berger vector, berger. Okay, berger vector is a vector of vector is the direction where the atoms will move. Okay, so it will move from here to here. Okay, and then next it will continue this direction. Okay, like this. Inilah. Okay, so after it's moved, this part is moved to this direction, this part will move this direction. Okay, so this is Berger vector. Okay, the concept of dislocation in the edge dislocation is if show you another example. Okay, like this. Dislocation motion is following the caterpillar behavior of move. When it moves to the front, it will lift up like this. Oh, sorry. Okay. If this atom would like to move to this part, it requires another atom to lift up. Okay, and this part will go to here, and later this part will touch the front position. Okay, how? Right. Okay, like this. When we give a load here, okay, when we give a load at this direction, okay, shear stress, this one is, these atoms doesn't have any bonding with the atoms at the bottom part. Okay, and if you give more atoms or more loads, okay, if you give more loads, these atoms try to break the bonding, and what happened is it will develop a bonding with the no, all bonding will uh, detach. Okay, will break the bonds because of the load or shear stress. Okay, and then what happened is, okay, initially this is the atom who freely does not bond with the atoms at the bottom part. Okay, when you force this first at top part of atom move to this direction, okay, this atom next will become not attached to the atoms at the lower part. Okay, and it's continuous. Okay, continuous breaking and reattach. Okay, the bonding. So what happened is this part of atoms is moved to this part. Move. So now it's like there are some permanent deformation. Okay, initially like this. Okay, this is first condition. This is last condition. So the shape will change. The shape of material will change. So if you have a straight road like this, you bend the roads. So means that the atoms move like this. Okay, it will move and it will change the shape. Okay, so now what you can see, it, yeah, from the flat, it will become curved because of the dislocation. Okay, so what happened inside the plastic deformation is actually dislocation movement. All right. So next is screw dislocation. Screw dislocation is okay. You can Google this information how screw dislocation is presented. But actually, for this screw dislocation, instead of having extra half plane in screw dislocation, the lattice itself is sheared. Okay, sheared because of the force, and then the motion of dislocation follow the helical paths. Okay, helical paths means that it's moving this part, and then the atom move, and then next when this region is go up, this region will go down. It will continue until this point move to this point. Okay, and then of course and so forth to the below. Okay, so meaning that it's continual change the atom motion from one lattice to another lattice to another lattice to another lattice. Okay, so it's following, it will, yeah, at the end it will become at the end this point will continues until as long as the load is not released, these atoms will move continuously. Okay, this one for screw dislocation, it doesn't contain half cell, extra half cell. Okay, and then next is planar defects. Okay, planar defects are the boundary that have two dimension and normally separated region of the grains. A planar defect is a continuous of the perfect crystal structure across the planes, Okay, if you like, if you watch the previous lesson video, okay, when we have a nucleus here and here inside the molten materials, let's say this is your mold, you have a nucleus, and when it grow larger and larger and larger, okay, this is grained, and when they meet each other at this region, so this one will be a grain boundary. It is actually a defect. Okay, disordered or discontinued structure, perfect crystal structure. So let's say it's forming a crystal structure, okay, like a cube here and also here. Okay, it is ordered structure. At this grain boundary, disordered. The grain boundary. Okay, inside the grain, it is ordered structure. Okay, phase boundary, grain boundary. Okay, stacking faults. These are related to planar or surface defects. Okay, phase boundary is something like, for example, if you have never got a lot yet. Okay, let's say in your materials, for example, you have a material microstructure like this. Inside it has particles. Okay, this is your material, for example, copper, nickel, alloy. And in your alloy, you add something, for example, like nickel carbide. Okay, nickel carbide. So this is phase A. This is phase B. Okay, so the boundary is around these particles. So it is also known as a planar defects. Okay, the phase boundary. Okay, what is grain boundary? Grain boundary is a boundary separating two small grain or crystal having a different crystallographic orientation. Okay, I have explained just now. So let's say this is a perfectly oriented like this direction. Okay, you can see here, and this one this direction. Okay, this one cannot join this orientation. Orientation A and orientation B, they cannot continuously form one straight bonding. So what happened is they form some kind of grain boundary. This is grain boundary. So what you can see, it is not ordered structure at the grain boundary. Okay, so the good thing about this grain boundary is, okay, if you look at this location movement stop here. Remember this location just now, I have explained this location. Okay, if this location easily move inside your materials, you will get plastic deformation. Can you explain to me what is plastic deformation? The permanent deformation means that if you bend your material, it will bend it. Okay, it will bend. Okay, so it's a change in shape. So these locations, what happened during the plastic deformation is dislocation. Means that this location move. Okay, let's say you have an extra plane here, which is edge dislocation. What is edge dislocation? It has an extra plane. So this extra plane, if you give a load anyway, shear stress or whatsoever, this will move, but it will stop at the grain boundary because the original orientation is not similar at the this grain boundary. So what happened? It will stop at the grain boundary. So if you want to make sure that your materials are not easily deformed by plastic deformation, so means that this one is always associated with soft property, okay, soft or ductile properties. If your material has high plastic deformation, meaning it has easily to be dislocated. The dislocation will be easily moved. So if you understand this is the behavior of your materials, which is soft materials. So if you want to increase the strength, make sure the dislocation is stopped easily. How? By creating more grain boundary. More grain boundary. If you have this more grain boundary, create more grain boundary. Making small grain is more grain boundary. Large grain maybe not so much grain boundary. So if you produce small grain boundary, so it means that you will provide ample of site or agent to stop the dislocation motion. Okay, phase boundary. Okay, I have explained just now. Right, this is phase boundary. Even though it has similar crystal structures, taken for its planar defect form, but there is a disordering crystallographic planes. Okay, this is to detail. Don't worry, you don't have to really read it. Okay, right. Planar defects, 2D sites of filled with atoms. Right, there are 4 types of defects. Okay, summary. Quickly, we go to the summary. One, dimensionless is point defect. 1 dimension is a line defect. 2 dimension planar. 3 dimension is a volume defect, which is basically in the casting. Okay, this defect can be affect properties of materials in terms of strength, ductility, as well as their electrical, chemical, and their degradation properties. And these are not always bad defects. Okay, I think that's all for today.